Hello, this is a presentation about navigation mesh generation pathfinding by Ryan Garvin and myself, Will Pitts. This research was part of CS380, Artificial Intelligence for Games at the DigiPen Institute of Technology. Earlier in the course, we learned how to pathfind on a 2D grid. But pathfinding on a 2D grid has a lot of problems that we realized wasn't going to make it viable for most professional level projects that we were on. For example, pathfinding on a 2D grid can result in weird, angular paths that need to be simplified and smoothed out. As a second case, there are many maps that we would maybe want to make that couldn't be easily simplified into a 2D grid. So, rather than trying to make everything into a grid and smooth out all the paths that we made, we figured, what if we just use a nav mesh instead? We could use that on more varied architecture, and we could draw lines much more cleaner and more optimally between point A and point B. Once we started working on pathfinding and nav mesh, we realized pretty quickly that in order to pathfind, we needed a nav mesh to pathfind on. And you can't always make nav meshes by hand. At the most extreme cases, procedurally generated games such as Enter the Gungeon and Duskers have randomly generated maps. And with maps such as these, we would need to switch to the map, not have any idea what's inside it, generate a nav mesh on the fly while we were loading in, and then pathfind on that nav mesh that we just generated. So our project flipped to automatic nav mesh generation and then pathfinding on top of that nav mesh. Now the first step of this was generating the nav mesh. In order to generate the nav mesh, we had a simple idea of what we needed to do. The first thing was we took our 2D grid and we used it to just break everything into triangles by dividing every square in half. We figured that with non-2D grid maps or maps that were resistant to 2D grids, we could get something relatively close to start a very, very basic nav mesh up. Now, the problem with having this very basic nav mesh, even though it was nice having one, is that it was way too complex for what we actually needed to do. Since we divided every square in half, all we really did was double the amount of work that our A-star Pathfinder had to do. So we needed to simplify this down, and we used a two-step process for that. The first was taking polygons on our nav mesh and just removing all vertices that weren't on the outside edge of the polygon. The second step, once we had the shell of a polygon, was the ear clipping method. And how that worked was we took any acute angles we could find on the polygon, we used the two edges that acute angle were a part of to make a triangle, and then we clipped that triangle off of the rest of the polygon. Rinse and repeating this over and over and over on polygons, we could simplify them into a nav mesh that used less vertices. And repeating this just upon polygons that we had on the nav mesh, we could make a much more optimal nav mesh. More complicated from a human perspective, but using less triangles, so simpler from a machine perspective. Now that we had our nav mesh, our second step was actually pathfinding on the nav mesh. And our first thought was to use an A-star algorithm in much the same way that we used on our 2D grid. Just instead of the grid, we would use the center of the triangles to pathfind on. This worked, but resulted in a path that wasn't going to be viable in professional level projects. It was too angular, it could cut through terrain, and it just wasn't what we needed to have. So we needed some way to make this path that we have from point A to point B better. And the method that we settled on in order to do that was the funnel algorithm. Now the funnel algorithm is relatively simple. First thing, we generate that path that you just saw between all the triangles. Once we have this path, we can get the edges that we cross on it in order to get an order of the edges that we cross in order to get from point A to point B. Once we have the edges, we don't care about the path anymore, we throw it out. Now using these edges, we create a funnel, a left and right side of all possible paths that we could take from point A to point B. Once we process an edge, we just move on to the next edge, narrowing the funnel as needed. But there are some problems that we can run into. For instance, take the next edge. When trying to draw the left side of the funnel, we cut through terrain. And we can't really use this pathfinding method if it means that we have to do terrain checks 1,000 times every single frame. But because this new path would actually widen the funnel instead of narrowing it, we don't have to worry about terrain checks. we can just use that point and extend the left side of the funnel, making it two different segments. And this means that we don't have to do terrain checks because we'll naturally wrap around any terrain that we may come across. Okay, so that's the left side of the funnel, but what about the right side of the funnel for this next edge? When we draw that, it actually crosses over the left side, so that the left side of the funnel is now on the right and the right side of the funnel is now on the left. Well, we can solve this problem too. We use the section that is crossed over and we turn that into a tail. Now that tail is actually what is going to be our finalized path. And we draw our funnel from the end of that tail so that instead of it being from the edge to the start, it's now from the edge to the end of the tail. This results in a left and right hand side that no longer crosses over each other, and we also know part of our finalized path. Continuing on, we process the last edge, and having processed all edges, we now have the very easy operation of just drawing a line from the end of the tail to our finishing line point. But there's an obvious problem that might come up. What if we can't cleanly draw a line from the point to the tail? This would result in one collision check, but it's still a collision check in the middle of our pathfinding. Well, we don't have to actually do that because it's the exact same as trying to extend through the square. Rather than, since this is on the left side of the funnel, we can just use the left side of the funnel as our finished path to draw around the obstacle and get from point A to point B without having to worry about anything. So the result of that on the path that I showed off previously is a clean, straight line from point A to point B across the Navmesh. So that's it. We generate a Navmesh, we make a path on that Navmesh, and then we're all good to go. So let's show a quick demonstration as to how our demo actually works. So in an open map like this, it's easy. When you're pathfinding in the same triangle, you can just draw a line straight from point A to point B without really having to worry about using the funnel algorithm at all. As soon as we cross a line in the Navmesh, we use the funnel algorithm, but in this case, since there's only one edge, it's a super simple step. All we do is draw a funnel from left to right, and then just immediately go straight to our end. But let's see what happens on a slightly more complicated Navmesh. Now this Navmesh is drawn on the fly as soon as I click the next map button in the top right. And we're able to pathfind, easy does it, straight across it. And we're able to pathfind on this map as soon as we generate the Navmesh. And we're able to pathfind on this map. And we're able to pathfind on this map. And all of these maps are generating their own Navmeshes on the fly as soon as we load the map in. Now to actually demonstrate a little bit better how this works, we'll use a simple grid. A simple maze. So, walking into the bottom right corner and then pathfinding all the way to the top left, you can see that our path hugs all the walls correctly, hugs all the edges correctly. Whenever it has to go a diagonal, such as from this point to this point, it just smoothly interpolates between the 2 points, all the way up to our finalized path so that we can walk no problem, hugging all the edges in the best optimal path that we're able to get. And even on large complicated maps, such as the second map that we showed, it is able to pathfind from the top left to the bottom right, hugging all the edges and using relatively few nodes to get from point A to point B as optimally as we possibly can. So, going back to the actual presentation, let's do a quick review as to what our project actually was. The first thing we did was we used the grid to generate the simplest possible Navmesh that we could generate, just dividing every square in two. Once we had a simple Navmesh, we used our two-step process, finding polygons and ear clipping them, to make it much more optimal by removing as many vertices as we possibly could have. Now that we had a better Navmesh, our next step is to do a normal A-star pathfinding on it by using the center of the triangles as the nodes in our pathfinding algorithm. Once we have a path, we take all the edges that it crosses and use those edges to do the funnel algorithm to get a perfectly clean path from point A to point B. And that's it. That's as simple as it is. 4 steps, generate a simple Navmesh, clean it up before we load in the map, A-star pathfind on the triangles, and then clean up with the funnel algorithm. So that was our research presentation. Thank you so much for watching. My name is Will Pitch, Will Pitts. My partner was Ryan Garvin. This was for CS380 Artificial Intelligence for Games, and I hope you have a good day.